Okay, so from today we will start to talk about forward and inverse kinematics. So what does forward and inverse kinematics mean? So before we start to talk about forward kinematics, so let's take a look at these two robotic arms. So we may see this type of robotic arms before. So for example, this one, and we may play with this type of robotic arms before. So for example, the first one, here we have a motor, and here we have a motor, and here we have a motor, and right here we have a motor, and we have right here we have another motor, and here on this controller, and we have 1, 2, 3, 4, 5. We have 5 buttons, and these 5 buttons are controlling these 5 motors. So for example, if you push this button, and you probably will be able to control one of the motor so that this robotic arm can achieve some motions. Okay? And this robotic manipulator is a similar idea. So actually, when we talk about robotic arms, when we talk about robotics, we want to answer 2 questions. The first question is, what will the end effector, this is the end effector, okay? This is the end effector. In this case, it is a robotic arm, and so here we have a grasper. And in some other cases, so for example, the industrial robotic arms, and you may have tooling, or you may have other type of tooling, okay? So the first question we want to answer when we do the robotic analysis is that, what will the tooling achieve with given motor control? So for example, in this example, if we give different position of these buttons, what is the final position of the grasper? In this case, of this grasper, which is the end effector, right? So if we want to answer this question, it means that, okay, so each of the motor is controlled by a human input, like what we did in the previous motor lab, right? Okay, so now instead of we only control one motor, in this case, we have 5 motors. We have 5 motors. So it means in your Arduino, you need to have 5 inputs to control these 5 servo motors. Okay, so if we give 5 human inputs, means we give 5 positions of the buttons, and we can control these 5 motors in 5 angles. So that, what is the final position of the end effector? Okay, so we want to understand that, and we also want to understand at each time point what should be the end effector's position if we give the parameters of these 5 motors. Okay, so if we want to answer these questions, so that is forward kinematics. Forward kinematics. It means we understand the motor control, means we give these motor variables, and what is the final position and final velocity of my end effector. The second question is that, okay, so now I have some tasks for the robotic arm to do. And then the question is how we're going to design the coding, how we're going to design the controller to control the motors so that we are able to achieve the desired positions of the tooling. Okay, so if we want to answer that, this is the inverse kinematics. Okay. So from the goals of the robotic arm, so we can see that, okay, so if we want to understand the goal, the final position of the end effector and the motors, we want to understand the relationship between these two, we have to do some definition and conventions. Okay, so So then let's start to talk about forward kinematics. Forward kinematics, again, it means we know we already gave the input to every motor. We already know the angles of every motor. Then we want to do the analysis so that we can finally understand the final position of the end effector. Okay, that is the question for forward kinematics. Okay, so to determine the position and orientation of the end effector, we given the value for the joint variables and the robotic geometry. Okay, so again, the forward kinematics, it is to answer the question of the final position and orientation of the end effector if we already gave the values of all the joint variables, and also we need to know what is the manipulator, which is the robotic geometry. And in a basic robotic arm, since now we start to learn the robotic arms, so we assume all the joints have 1 degree of freedom. Degree of freedom means it either a revolute joint or a prismatic joint. Okay, so a revolute joint means it can only do rotation. And for a prismatic joint, it means it can only do one translational motion. And the references attached to all the joints means, okay, so we may see this schematic before and from the first lecture of robotic introduction, right? And each revolute joint is represented by a cylinder. And how about prismatic joint? Do you still remember that? A prismatic joint in a robotic analysis, we use a cubic to represent a prismatic joint. Okay? And each joint need a coordinates so that we can do a accurate analysis. So let's review a little bit. So this robotic arm, and we have seen that before. And in this robotic arm, we have one revolute joint, and here we have one revolute joint, okay, which is the base here, okay? So if we extract the model of that right here and the base, we have a one revolute joint, and here we have one revolute joint, which is kind of the shoulder, and here we have the elbow, which is right here, okay? So this robotic arm, this manipulator, it has 3 revolute joints. So this is also called RRR. Okay? And this manipulator, we have 1 revolute joint. And right here we have 1 revolute joint. And this is 1 prismatic joint. Okay? So means here, if we extract the model of this robotic manipulator, we have 1 revolute joint, 1 revolute joint, and 1 prismatic joint. So this is called RRP. And this one, the SCARA manipulator, which is commonly used, it has 1 revolute joint and 1 revolute joint and a prismatic joint. So it is also a RRP. But in this case, we have these two axes, they're parallel to each other. And this one, this manipulator, we have 1 revolute joint on the base. And this thing, it can move, and this thing, it can do translational motion. So 2 translational motion. So it means 1 revolute joint, 1 prismatic joint, and 1 prismatic joint. So this is a RPP manipulator. And next one. And for this one, and it is a little bit unique that all the 3 joints are prismatic joints. Okay, so this one is called PPP. We have learned this before. So this is just a quick review. So from this robotic robotic arm modeling, robotic manipulator modeling, so we can see that to do the accurate robotic analysis, first of all, we need to extract the joints. And then we give each joint a coordinates so that we can do further analysis. Okay, so again, for forward kinematics, we try to understand the final position and the orientation of the end effector with all the known joint variables and the robotic geometry. Okay, so this is a analysis, means we already know the given joint variables, and then we want to know, okay, so what is the final position and orientation? Again, what is inverse kinematics? Again, what is inverse? So inverse kinematics means we already know the desired position and orientation of the end effector. We go back to do the analysis so that we can extract the joint variables. So that is a inverse. Okay? So for these joint variables, in this case, we have 3 revolute joint. So we have this robotic arm is a RRR manipulator. All these revolute joints, we can use a Arduino and a motor to control that, which we have done that in our lab. Okay, so for our lab, we have now, I believe we are able to control each motor to achieve a theta, which is a rotation. So it means if we want to achieve a final robotic arm, we can do the assembly of multiple robotic motors, right? And so that we can do a quick assembly. Okay. So before we start to talk about the coordinates transformation, so let's do some robotic conventions. So this is, you need to quickly understand, and we need to be able to mark these conventions, these numbers of joints and links, so that we can do further analysis. So for the robotic conventions, a manipulator with n joints has n+1 links. Okay, so this is obvious that, okay, so if we have, say, 3 joints, it means that these 3 joints must connect 1, 2, 3, 4 links. On both sides of one joint must connect 2 links, right? So it means that we always have n+1 links if we have n joints. Okay, the second is joint. We define the robotic manipulator. In the robotic manipulator, we number the joints, starts from 1 to n. Okay, so for example, in this case, we number it as 1, 2, 3, which is the joint. Okay, the joint number 1, 2, 3. And we define the link number from 0 to n. Okay, so in this case, we define 0, 1, 2, 3. Okay, so that we have n+1 links if we have n joints. Okay, because we have the 0. And a joint I connects link n-1 and link I-1 and link I. Okay, so for example, this link 1, it is linking 0 link. This joint 1, it is linking link 0 and link 1. Okay, and this joint 2 is connecting link 1 and link 2, right? So it means that the joint I connects link I-1 and link I. Okay, so this is the link. And next, the coordinates. So the coordinates is defined on the joint. Okay, so the coordinates must be defined on the joints. Each joint each joint has one coordinate, so that we're able to see the joint variable, either a theta for a revolute joint or a translational motion for a prismatic joint. Okay, so the coordinates of joint I is the coordinates I minus 1. Okay, so here we must be very careful. So this is the joint I, but we use the coordinate 0 on the joint I, and we use coordinate 1 on joint 2, and we use coordinate frame 2 on joint 3. Okay, so we always use I minus 1 coordinates on the joints I. Okay, and when joint I are actuated, link I moves. Okay, so for example here, if the joint 1 is actuated, the link I moves, right? The link I moves. Okay, so it means that the next link is moving if the joint is moving. Okay, so we can see that, okay, so if joint 2 is actuated, the link 2 is moving. Okay, and if link 3 is actuated, joint 3 is actuated, link 3 moves. Okay, so it means when the joint I is actuated, the next, which is the link I moves. Okay, and also each joint has a joint variable. This joint variable is either a theta or a d. If it is a revolute joint, the variable is a theta. If the joint is a prismatic joint, then the joint variable is a d. Okay? That's easy to understand because each joint has 1 degree of freedom. 1 degree of freedom means we can use one parameter to describe one joint motion. So it is either a rotation, one rotation, which is a theta, or a translational motion is a d. Okay? Once we define the theta and d, and we can quickly understand the next link's motion with regard to the previous links and joints. Okay? And another thing in the robotic conventions is the transformation matrix. Previously, we have learned homogeneous transformation. So that is the general concept of transformation. So now when we talk about robotic analysis, then we have to do a little bit different conventions. So the homogeneous transformation between frame I and frame I minus 1, we define that as AI in robotic analysis. So if a general analysis, so this is I minus 1, right? And in robotic convention, we write it as IAI. Okay, so this is equivalent to the general definition of I minus 1. Okay, and this homogeneous transformation, if we write down the general definition of this homogeneous transformation, obviously here we have the rotation matrix of I minus 1, and here we have the translational motion d I minus 1. Okay, so in this case, we just talk about this d is equivalent to the origin translational motion, so we use O instead. So this is I minus 1. Okay, so again, in the general definition, which we just learned last lecture, and this is I minus 1. Okay, in the robotics conventions, we use AI as the HII minus 1. And it is a function of joint variables. Okay, so means the rotation matrix here, this RII minus 1, or the motion vector of the origin, which is OII minus 1, these two, if we talk about the variable to define these two matrix or vector, this is a function of the QI, okay, which is the joint variable. So QI is a general definition of joint variable. It could be, this QI could be a theta I, which is a prismatic joint, or a DI, which is a prismatic joint. Okay? So it means that we can use the joint variable, and again, these two joint variables, we can actually use a motor and use Arduino to directly give these joint variables. Okay? If we give these joint variables, we can calculate the homogeneous transformation matrix between the frame I and frame I minus 1. Okay. And the transformation matrix, now instead of we use H, in robotics convention we use T instead. This is just H. It's equivalent to H, but we just use another convention. Okay, so T, J, I defines the relation between position and orientation of any two joints. Okay, so this is equivalent to the HI I minus 1, okay, because this is a homogeneous transformation matrix. And this TJI, it is equals to the homogeneous transformation, which is HI plus 1, and this is HI plus 1, I plus 2, HI plus 2, HI plus 3, and blah, 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 until finally you have HJ minus 1, so that we can cancel out these subscript or the superscript. So finally we have this I and J left. Okay? So here in the robotics conventions, these T, J, I, it means the relation which is a sequence of the homogeneous transformation multiplication, and this thing can be calculated by all these homogeneous transformation matrix multiplication. Okay? And by definition, this TJI, it relates the position and the orientation of any two joints. Okay. And if this I is less than J, okay, I is less than J. And if I equals to J, means they're the same, right? They're the same. If they're the same, it's just the I, which is a 1, 1, 1, 1. Right? Okay. And if I is larger than J, then it is just the inverse matrix of the Tij. Okay. So the end effector. The position and orientation of the end effector is a constant in the last frame. Okay? So the end effector, if we want to understand, okay, again, the end effector is our goal, right? It is our goal. And if we want to understand our goal, which is the position and orientation of the end effector, we need to know the last frame, the last coordinates, which is frame n. Okay? And the position and orientation of end effector with respect to the base frame, which the H 0, right? The base frame is frame 0. We always start from coordinate 0, okay? The base frame, which is joint 1, right? Joint. When we number joint, we number from 1 to n. Okay? So if we number links, we do 0 to n so that we have n joints, we have n plus 1 links. And the coordinates, if we number coordinates, we number from 0 to n minus 1 for all the joints. And the last coordinates of n, it is not for the joints, it is for the n effector. Okay, which is tricky, right? Which is tricky, but it's clear. Again, so if we define in the robotic conventions, we number the joint from 1 to n. We number the links from 0 to n. We number the coordinates for each joint. Each joint, if it is 1, then the coordinates is 0. If it is joint n, then the coordinates is coordinates frame n minus 1. So if a robotic arm, it has n joints, it means it has n plus 1 links, it has n joints, it has n coordinates because each joint has 1 coordinate. And here, if we want to add the n effector, we add 1 coordinates so that we can finally describe where is it by a clear coordinate. So that is the goal. Okay? So finally, if we want to clearly control a robotic tooling, which is the n effector, we want to finally understand what is this coordinates, this n effector's orientation and position in the base frame, So which is the frame 0, okay? So that is easy to understand if we have a final reference. If we understand the n effector's position and orientation in the base frame, then that is very clear that we can quickly understand where is it in the world space, right? Okay, because the base is the world coordinates. It is not rotating, it is not moving anything, it's just in the base, it's on the base, it's the world coordinates. Okay? And ON0 is the coordinate of the origin of the n effector with respect to the base frame, okay? And Rn0 is the rotation matrix, defines the rotation of the n effector frame n with respect to the frame, the base frame, okay? So, which is the rotation and displacement, which is the motion. Okay, so it means no matter what is the homogeneous transformation in between all these joints and transformation. So finally, if we can have this rotation and translational motion with respect to the base, which is the world coordinates, we're all set because this is the final goal we want to achieve. We want to achieve the n effector, the tooling's position and orientation in the world coordinates. That is our final goal. Okay? And the key is we will be able to calculate this Tn0, okay? So which is Hn0, but in robotic conventions, we use T instead. We use T, okay? And this T is a sequence of homogeneous transformation matrices multiplication. So each is a function of the corresponding joint variable, this Q Q1, Q2, Qi, and again, this Qi is the joint variable, so it is either a theta I or a di. This is for a revolute joint, and this is for a prismatic joint. Okay. And we recall this TJI. Again, the TJI, we have just talked about it. So this TJI is not for the end effector, but this is for something in between, okay? So in the robotic arm, obviously there are a few joints. They're not just one. So for example, the first photo we saw, which is kind of a toy that we have played with it before, and for that toy, it has 5 joints. So it means if we want to understand, so for example, the joint 2 and joint 4, and that is T42, okay? So, anyway, this TJI, it is a homogeneous transformation matrix relating the frame J and frame I. Okay, and it is a sequence of homogeneous transformation matrix multiplication. And again, this is the rotation part, and this is the translational motion part. Okay, this is the rotation matrix, and this is translational motion. And this rotation matrix, that is also, we can do a sequence of rotation matrix multiplication. But for the coordinates vector, which is the displacement, the positioning vector, which is equivalent to D, but this is the position of the origin. And this thing, we cannot use this formatting. Instead, we have to use this vector equals to this vector plus the rotation matrix times this vector. Okay? So it means it cannot use the a sequence of multiplication of some matrices. We cannot do that. Okay, so before we talk about the further conventions, so let me stop here, and then we will talk about the DH conventions.